All right, we're going to talk about the divergence of a vector field. First of all, what's a vector field? Well, a space with coordinates x, y, z, and then to each point in space you assign a vector. So if I imagine having some space coordinates x, y, and z, and then to each of these points I'm going to assign a vector v. And so this is called a vector field. So it's basically a vector that is a function of space. And a good example of that would be the fluid velocity in the ocean, right? So we can pick any point in the ocean and there will be some current, and that velocity of the mass at that point is a vector, right? It has a magnitude, a speed, and a direction, and so therefore it's a vector. And we can define for each point in the ocean a vector which corresponds to the velocity, and so the velocity of the fluid in the ocean is an example of a vector field. All right, so what do we mean by the divergence of a vector field? Well, to think about that, we need to think of a volume. So I'm going to pick a volume, I'm going to pick it to be a box. So I have a box over here. And what the divergence is, the outward flow through the surface per unit volume. So the divergence is of V is the outward flux of V through the boundary dV of a volume V per unit volume. So if this box has volume V, what we would do is calculate the outward flux from all the 6 sides and then divide by V, and then take the limit where we shrink V to 0, and that will define the divergence of the vector V. All right, so to start thinking about this, it's useful to first think about what is the flux through a surface. So I'm going to define the flux through a surface in this way. So if I take a little patch of surface area, patch like this, and this little patch of area is going to have an orientation, right? I can tilt it around. So we can define the orientation. That's better. This is n hat. So there are two. You can also have the n hat in the opposite direction. So surface areas, they have an orientation, and you can, if you look at it from the other side, is a negative orientation. But as long as we pick one and we define it in that direction, then we know what we're talking about. All right, so the flux through that patch is going to depend on the vector v, and what we want to calculate is how much of v flows through that surface. So if I now pick some vector v, let's suppose v is going in this direction. This is v, right? So there's going to be a component of v which is parallel to n hat, and there's going to be a component which is perpendicular to n hat, right? In other words, there's part of v that flows along the surface, and there's part of v that flows through the surface. And so the only part we need to know about is the part that flows through the surface, the part that's of the vector v, the component of v that's in the plane of the little patch doesn't flow through it, it just flows parallel to it. So we can decompose v into 2 bits, v dotted with n hat times n hat. That's the part that goes along n hat, and plus everything else. So everything else is just v minus this part. And so this bit here, I'm going to call that v perpendicular, because it's perpendicular to the surface, plus v parallel, because it's parallel to the surface. Now, maybe this is confusing a bit. So this is the part that's perpendicular to the surface, but parallel to n hat. This is the part that's parallel to the surface, but perpendicular to n hat. So we have to be careful what we mean by parallel and perpendicular. Here I mean relative to the surface. All right, so if we want to get the flow through the surface, what we will do is we just worry, this one doesn't go through, so we just worry about this one. And the amount of flux through the patch is going to depend on the size of the patch, right? If we have a tiny little patch, there'll be only a little bit of flow. But if our patch is very big, we'll get a lot more flow. So an intuitive example of that is you open the window and you let the air flow through. If you have a big window, then you'll have a lot of flow coming through, and if you have a tiny window, you'll have only a little bit of air flowing through. So the flux phi, right, is going to be equal to, and dotted with n hat, right? That's the part that's perpendicular that goes through, and multiply that by the area, ds. And this can also be written as just v dotted with ds vector, where ds vector is a vector which is parallel to n hat and whose magnitude is ds. So we just scaled the unit vector to give us the by ds. So it's in the direction perpendicular to the surface, and the magnitude is proportional to the area. So this is the flux through the surface, and this is how you can express it in terms of the little surface patch area. This part here, right, v dot n hat, is just this bit. Okay, now if we imagine taking a bigger volume, we can, if we want to do the divergence, we'll need to know the flux through the outward flux through a surface of a volume. So what we'll do to define the divergence is we'll pick a simple volume, a little rectangular box, and we're going to calculate the outward flux through all the 6 faces, and then take the limit where that volume goes to 0 ounce. Like this. And the area of each side, so if this width here is dx, this width is dy, and this one is dz. So the volume dv is dx, dy, and dz. That's the volume of that box. The area of the sides, there's going to be 6 sides. The area of this one, right? So the area perpendicular to the x-axis, that will be this side, or that side will be equal to dy times dz. The area perpendicular to y hat is going to be either this front or the back face, and that's going to be equal to dx times dz. And then finally the area perpendicular to z hat, that's going to be the bottom or the top, is going to be equal to dx times dy. And now we want to get the flux through all these surfaces, the outward flux, and so we want to take the vector v and dot it with the normal to each face. So we want to get the flow out through it, this side here, and this vector that's pointing out of this face is just the y hat vector, right? And the one pointing outside, well actually it's minus y hat. The one pointing outside on this one is minus x hat. The one through the other side is plus x hat. The one out through the top is z hat, and the one out through the bottom is minus z hat. And same with the one on the back side here that we don't see. That's going to be plus y hat. So these are all the outward unit normals. And so it's easy now. If we take v dotted with z hat, for example, all we get is the z component of v. And if we take z dot v hat on this side, we get just minus the z component of v. On this side, we get plus the x component of v. Here we get minus the x component, minus the y component, plus the y component, and so on. So let me write down what the components of this are. This is going to be vx, vy, and vz. So these are the 3 components of the vector v. And now the divergence, which we write as divergence, is div dot v. That's how we write the divergence, and that's equal to 1 over the volume. We're going to take the limit, so I should write the limit. The limit, as delta v goes to 0, of 1 over delta v times, and what do we do? Times the outward flux through the box. So we're going to do it one face at a time, so let's do the faces perpendicular to the x-axis. So that will be the component of v in the x-hat direction coming out of the box, so that'll be vx, and that's vx evaluated at x plus dx, y and z, minus the flow out the backside, vx and x, y, and z, right? So if this point is at x, this one is at x plus dx, so I put x plus dx, because they're not exactly at the same place. And then this quantity here gets multiplied by the area, which is dz and dy. dz, dy. And then I add the outward flux through the faces perpendicular to the y-axis. So that's vy, x, y plus dy, z. That's the outflow out the back, minus the outflow out the front, vy of x, y, and z, and this time the area is dx dz, right? Dx times dz is the area of that cross section. And the last term is out through the top and the bottom. So out through the top is vz, x, y, and z plus dz, minus vz at x, y, and z, and then the area is just dx dy. And then I can close my parenthesis. And now I use the fact that dv is just dx, dy, dz, and so when I divide through, the dz, dy will cancel, and I'll just be left with the first term divided by dx. Here, the dx, dz will cancel, and I'll just be left with this term divided by dy, and here divided by dz. So this will then be equal, and I'm going to use the eraser, because I'm running out of board space, but in your notes you could just copy over. So after I divide through, the dv goes away, and this becomes over dx, and this goes away, cancels out. And this one will be over dy, and these two will cancel out in this term. And in the last term, this will be dz, and then these two will cancel out. And then when I take the limit, then what you get is the partial derivative of the x component of v with respect to x. Here, the partial component of the y component of v with respect to y, and same thing down here. So what I get is that the divergence of v in Cartesian coordinates is just dvx dx plus dvy dy plus dvz dz. And this is the divergence. Right? And what it means, it's the outward flow, or the outward flux of v per unit volume. All right.